Imagine that you've peered into the darkest depths of space, to where light has been traveling toward us for more than 13 billion years. And instead of the expected emptiness and faint glimmers of the first stars, you saw something completely impossible: little red dots that simply shouldn't exist. This is exactly what happened when the James Webb Telescope turned its golden gaze toward the edge of the observable universe. What it saw called into question everything we knew about the birth of the cosmos. When in December 2021, James Webb finally launched into space after decades of waiting, astronomers around the world held their breath. This $6 billion instrument promised to look further than humans had ever looked before. Its 6.5-meter diameter mirror and unique ability to see in the infrared spectrum were supposed to show us the infant universe, as it was just a few hundred million years after the Big Bang. We expected to see the timid first stars, small galaxies just beginning to form. We expected confirmation of our models. Instead, we got a cosmic mystery. The very first deep images brought a surprise. Among the billions of galaxies captured in the images, astronomers noticed strange objects, tiny red dots, barely distinguishable even for such a powerful telescope. Red dots in space images are nothing new in themselves. Distant galaxies often appear reddish due to cosmological redshift. When the universe expands, light from receding objects stretches, shifting toward the red part of the spectrum. The farther the object, the stronger the shift. This is the ABC of modern cosmology. But these dots were too red and too bright for their age. When scientists began analyzing the spectra of these mysterious objects, the picture became increasingly disturbing. The redshift showed that we were seeing these dots as they were 400 to 600 million years after the Big Bang. This is incredibly early. The universe was then less than 5% of its current age. Imagine a 3-week-old baby who can already run marathons and solve differential equations. That's about the same level of surprise astrophysicists experienced. But the real shock was yet to come. The brightness of these objects in certain spectral ranges indicated that they must be incredibly massive and active. We're talking about masses in the billions of suns, about luminosities that eclipse entire galaxies. In such a young universe, this seemed absolutely impossible. According to our models of structure formation in the universe, supermassive black holes grow gradually. They start with the collapse of the first massive stars, creating stellar mass black holes, say tens or hundreds of solar masses. Then these black holes slowly, over billions of years, consume surrounding matter, merge with each other, gradually gaining weight to millions and billions of solar masses. This takes time, a lot of time. Even in the most optimistic scenarios, when a black hole devours matter at the maximum possible rate, the so-called Eddington limit, it requires hundreds of millions, if not billions of years, to grow to such sizes. And these red dots simply didn't have enough time for this. The universe was too young. It's like finding a newborn in a maternity ward weighing 100 kilograms. The laws of physics seemingly forbid such a thing. The first and most obvious hypothesis was that we're seeing supermassive black holes actively consuming matter. When matter falls onto a black hole, it forms an accretion disk, a giant vortex of incandescent plasma, rotating around the event horizon. Friction in this disk heats the matter to millions of degrees, causing it to radiate a colossal amount of energy. We call such objects active galactic nuclei, or quasars. They can shine brighter than trillions of suns. This is exactly what we seem to be seeing. But how did these monsters manage to grow so quickly? One idea suggests the existence of so-called direct collapse seeds. In the special conditions of the early universe, in regions with huge clouds of primordial hydrogen and helium, black holes could form immediately with masses of hundreds of thousands or even millions of solar masses, bypassing the star stage. It's as if a child were born immediately as a teenager. Such a scenario requires very specific conditions, but it's at least theoretically possible. Starting with such a massive seed, a black hole could grow to billions of solar masses in a relatively short time. Another possibility is super-Eddington accretion. Perhaps in the early universe, black holes could consume matter much faster than standard models allow. The Eddington limit arises because radiation from falling matter creates pressure that pushes away new matter. But if matter falls in very dense streams or at certain angles, this limit can be bypassed. A black hole could grow tens of times faster than normal. This is a controversial idea, but James Webb's observations force us to consider even the boldest options. However, the more data accumulated, the more complex the picture became. Some of the red dots showed strange features in the spectrum. The emission lines were unusual. The brightness ratio in different ranges didn't quite match what we expect from quasars. And here another completely fantastic hypothesis entered the scene. What if these aren't black holes at all? What if we're observing something we've never seen before: dark stars? The concept of dark stars was proposed even before the launch of James Webb, but was considered purely theoretical exotica. The idea is this: in the very early universe, when the first stars were forming, gas clouds could contain a significant amount of dark matter particles. We still don't know exactly what dark matter is, but we know it exists because we see its gravitational influence. One theory suggests that dark matter consists of particles called WIMPs, weakly interacting massive particles. These particles can annihilate when colliding with each other, converting into ordinary energy. Now imagine a young star inside which a huge amount of dark matter particles has accumulated. When these particles collide and annihilate, they release colossal energy, much more than ordinary thermonuclear fusion. This energy can support the star, preventing it from collapsing, and makes it shine incredibly brightly. Such a dark star could be millions of times more massive than the Sun and shine like an entire galaxy. And most interestingly, its spectrum would be slightly different from that of an ordinary star or quasar, which would explain the oddities we see in the red dots. If this hypothesis is correct, the consequences are stunning. First, it would mean we finally received direct observational confirmation of the nature of dark matter. Second, it would completely change our picture of how the first luminaries in the universe formed. Third, it could explain where the seeds for those very supermassive black holes came from. When a dark star exhausts its dark matter reserves, it collapses, leaving behind a black hole of already enormous mass. But there's also a third possibility that astrophysicists speak of in hushed tones, afraid of being branded heretics. What if our standard cosmological model, the lambda-CDM model, on which our entire understanding of the universe's evolution is based, is fundamentally wrong in some way? What if the Big Bang didn't happen quite as we think? Or what if dark energy behaved differently in the early universe? Or the expansion rate was different? Some researchers suggest that the red dots may indicate that the early universe was denser and hotter than we assumed, which allowed structures to form faster. Others believe that primordial density fluctuations, those tiny inhomogeneities from which all galaxies and clusters grew, were stronger than the cosmic microwave background shows. These are radical ideas that would require revising many basic assumptions. But this is exactly how science develops. When observations contradict theory, the theory must be changed. By early 2026, enough data had accumulated for more detailed analysis. New spectroscopic observations allowed more precise determination of the red dots' characteristics. It turned out that among them are different types of objects. Some indeed look like supermassive black holes growing incredibly fast. Others show signs that may indicate dark stars or some hybrid objects. Still others remain completely mysterious, not fitting into any of the models. What's particularly exciting is that we're in the midst of a scientific revolution. Each new cycle of James Webb observations brings fresh data, Astronomers around the world are analyzing spectra, building new models, testing hypotheses. Heated debates are taking place at conferences and in scientific papers. Some defend traditional explanations, proposing increasingly sophisticated variants of rapid black hole growth. Some advocate for dark stars, seeing in them the key to solving the nature of dark matter. And some call for a bold revision of cosmological foundations. The truth will probably turn out to be more complex than any simple explanation. Perhaps the red dots represent a mixture of different phenomena. Perhaps some of them are indeed direct collapse black holes. Others are dark stars. Still others are something completely unexpected. Nature rarely fits into simple schemes, especially when dealing with the extreme conditions of the early universe. What can we say for certain? The discovery of red dots shows that the early universe was much more complex and amazing than we assumed. It was capable of creating massive, bright objects incredibly quickly. The mechanisms of this rapid growth still remain a mystery, but the very fact of their existence is indisputable. This isn't an observational error, not a data processing artifact. The red dots are real, and they demand an explanation. The future of research looks exciting. James Webb will continue collecting data, gradually expanding our sample of these mysterious objects. New telescopes, such as the next-generation ground-based giants, will join the hunt. Theorists will refine their models, possibly discovering new physics in the process. In a few years, we'll know much more. Or perhaps we'll face even deeper mysteries. The story of the red dots reminds us why we explore space. Every time we point a more powerful telescope at the sky, we risk discovering something that will overturn our ideas. Every new discovery isn't just adding a fact to a textbook, it's an opportunity to rewrite entire chapters. The universe constantly surprises us, reminding us that we're only just beginning to understand its true nature. And this is the real beauty of science, the willingness to revise our views in the face of new evidence. The excitement of searching for truth, however unexpected it may turn out to be.